Okay, we're back to our exam review, and we're up to problem number 30. And the question is, considering the graph of this function y equals x cubed, this is called our cubic. It's one of the basic functions in your library of functions, which you should have known from last year. Which of the following is most similar to the behavior of the graph around the origin? So how does this curve pass through the origin? At a 45-degree angle, does it pass through vertically? Is the curve actually looking like a line if you zoom in enough, or does it pass through horizontally? And we have our calculator here. I suppose we can go ahead and put in y equals x cubed and just look at it in a standard window. And sure enough, it appears to be choice B. That is the right answer. By the way, if we zoom in here, zoom to enter, you'll see that as you get closer and closer to the origin, I'll zoom in one more time, this does appear to be horizontally passing through the origin. Okay, we'll be looking at our library of functions over the next day or two because we will be testing those before the semester ends. Okay, number 31. We have a graph y equals x plus 2 quantity cubed, and the parent function that we know. Let's see if we can get a couple of pictures going here. Okay, so here's our parent function that we just looked at, y equals x cubed, passing through the origin like that. And the question is, what does y is equal to x plus 2 quantity cubed do? It shifts at 2 units, and the question is 2 up, down, left, right, or some sort of weird reflection? This is simply a shift left. If we had our tick marks here, you would find the graph would move 2 units to the left like that. Okay. Go back to our standard window here. If we put in a second function, y equals parent x plus 2 cubed, sure enough, we see that it's shifted 2 units to the left. The correct answer is C. Now, you should know basic transformations, up, down, left, right, reflections, and whatnot. Number 32, what's the domain of this function, and what's the zero of this function? Again, here's the sketch. Remember, it's our parent function shifted 2 units to the left. So here's our cubic, y equals x cubed, and y equals x plus 2 quantity cubed looks like that. So the domain is certainly all reals. Remember, domain is simply the values that you can put in for x and make this defined. You can put any positive, negative, or zero in there. So the domain is all reals. You can also think of it graphically as the horizontal extent. So sure enough, there are points going from positive to negative infinity. What's a zero? Remember that zero of a function is synonymous with the x-intercept of the graph. And it's pretty clear that this hits at -2. Well, x is equal to -2. Okay, pretty easy if you have the picture there. Number 34. Once again, we have this discussion about y equals x plus 2 cubed. We have the picture over here. Let me get rid of the blue one. We'll delete that. And so all we have is our graph y equals x plus 2 quantity cubed, and the question is it even, odd, or neither? Okay, even functions are like functions, or similar to functions like y equals x squared, or y equals the absolute value of x. These are functions that, if you look at their graph, y equals x squared looks like this. Let's make this +1 just to make it a little bit different. Y equals the absolute value of x +1, that would be the absolute value graph, which you should know looks like this, except we're going to shift it up 1 unit, so we'll just raise it up like that. But in both cases, the graph is symmetric about the y-axis. And certainly when you look at our function here, this one is not symmetric about the y-axis. It looks like that. Okay. Odd functions. Well, oh, by the way, this coming semester, we're going to be studying a number of functions that are even. For example, one of the functions we'll study is called the cosine function. And the graph of the cosine function looks like this. It's a wave, and it is symmetric about the y-axis. You'll notice that the left and the right side are the same. Okay, cosine function, that's an even function. Odd functions. Odd functions would be like y equals x cubed, or y is equal to the cube root of x, for example. X cubed, or y is the cube root of x. And again, these are in your basic library of functions. You should know what they look like. Y equals x cubed, well, we've already seen. It looks like that. Now, it's not symmetric about the y-axis or the x-axis, but rather symmetric about the origin. So imagine a point on this graph. Here's a point 2, 8. There is a symmetric point down over here in the third quadrant, which would be -2, -8. This is called point symmetry. You can also think of it as rotational symmetry. If we can spin the, see if I can do this and make it come off right. If we take this and actually spin it around, it should line up like that. Okay, so rotational symmetry about the origin. And again, this coming semester, we're going to study a number of functions that are odd. For example, the sine function. Sine function is another wave, similar to the cosine, but this particular wave is symmetric about the origin. So if I could imagine reflection here, let's see if I can, oops. Let me see if I can grab this whole thing. I guess I can't. Anyway, I was going to rotate this around the origin. The sine function is an odd function. And again, notice our graph that we're dealing with here, this shifted cubic, y equals x plus 2 quantity cubed. It is neither symmetric about the y-axis, nor is it symmetric about the origin. So this is, in fact, neither even nor odd. Most functions, by the way, are neither even nor odd. Okay, number 35. To reflect, here's our parent function again, reflect the graph y equals x cubed about the x-axis. Okay, so what we want to do, if we think about this now, we have our parent function y equals x cubed, which looks like this, and we want to reflect it about the x-axis. This part in the first quadrant, we want to head down into the fourth quadrant, and this part that's in the third quadrant, we want to head up into the second quadrant. So we end up with a picture that looks like this. And so how in the heck can we make that happen? And we have some choices. We do have our calculator here. Let me go back and look at, let's see, we'll put in y equals x cubed again, and we'll get rid of that one. Okay, so there's our parent. And the choice A says replace x with the opposite of x. So let's just throw that in here. The opposite of x, I'm using the opposite sign, not the subtraction sign. And I want to cube that. Now let's look at that graph. Well, sure enough, that does it. Okay, so this seems to work okay. But choice B says maybe we can replace the entire function with its opposite. So let's get rid of that one, and we'll try the opposite of y1. And I can actually go into vars, y vars function y1. I can choose that. And here's that graph. And sure enough, it does the same thing. By the way, if you don't like to use that y1 notation, you don't have to. We could have done the opposite of the function x cubed. Notice here the minus sign is out in front, but sure enough, that graph does what we want it to do. So this also works. Replacing x with the absolute value of x so that the equation becomes the absolute value of x cubed. I suppose we could try that and see what happens. Let's see, we'll do a parent first, and then we'll throw in the absolute value, which is under math number, and then we'll put in x. We'll close the absolute value, close the parent, and then cube. And here's that picture. And no, that does not do what we want it to do. By the way, this idea of replacing the x with the absolute value of x, you'll see next year in calculus. One of the functions we look at quite a bit is the natural log of the absolute value of x. Sort of an interesting transformation. What it does is it takes everything that's positive x values, and just reflects it about the y-axis. So we know that the natural log graph looks like that. If we wanted to graph the natural log of the absolute value of x, everything that's got positive x's, this entire green curve, is going to be reflected about the y-axis, and we end up with that. So we actually get both pieces. I'll throw that in here just to sort of demo. Again, you'll study it next year, natural log, math, number, absolute value of x, close the absolute value, close the log. And there's the graph. No, it doesn't hit at -2, right? We saw that earlier. This goes all the way down to -infinity. Okay, so the correct choice to this particular problem was, in fact, choice D. That was probably one of the harder ones on the exam. If you got it wrong, hopefully you understand what happened. The only real zero of this function, okay, so this is another transformation. We have x cubed plus 8. X cubed plus 8, you should realize that's a translation up 8 units. So 1, 2, 3, 4, 5, 6, 7, 8. So we have our parent function y equals x cubed going through the origin like that. And then moving it up 8 units, we have that picture there. And the question is, what's the zero, right? And so again, zero of the function is the same as the x-intercept. So where does this hit down here? I don't show it on my graph. It does hit at -2. We know that. You can also, instead of the real zero of the function, remember that's the solution to this equation, x cubed plus 8. So take 8 from both sides and raise both sides to the 1/3 power. So that's the cube root of -8. And that's -2. Okay. Pretty straightforward problem if you understand zeros of a function, x-intercepts of a graph, solutions to an equation equal 0. Number 37. Well, here's our x cubed plus 8 again. Remember, we saw this in one of the warm-ups. Shame on you if you didn't get it then. We have a sum of cubes. This first sign is positive, and the second sign has to be negative. So this is the one we want right here. Okay. And again, if you didn't know or you weren't sure, you could have distributed all these out and find the one that simplifies to x cubed plus 8. 38. A rational expression can be simplified by division. What does this mean? Again, we saw this in the warm-ups. And just to recall, if we have 3 divided into 21, and we know it goes 7 times with 0 remainder, what does that mean? Well, it means 3 times 7 is 21. So in this case, this x plus 2 times the x squared minus 2x plus 4 does in fact equal x cubed plus 8. The correct choice is A. The fact that we have a 0 remainder also says that we can clean this function up if we wanted to. You might want to think about this x cubed plus 8 over x plus 2 could be thought of as x plus 2 times x squared minus 2x plus 4 over x plus 2. And then you can cancel the common factors, which says that this rational function will have the same graph as this parabola, except for the one point that we canceled out. So this is the same, x not equal to -2. And we'll see that in a subsequent problem. Okay, number 39. This function has no zeros. By the way, since we're working with it, let's go to our calculator and dump it in here. We've got x cubed plus 8 divided by x plus 2, x plus 2. Okay, x cubed plus 8 divided by x plus 2. Here's the graph, standard window. And sure enough, it has no zeros. Remember, zeros of a function is the same as x-intercepts of the graph. This does not at the x-axis. So what does this mean when it has no zeros? What it means is that the graph has no x-intercepts. We've got that. And the fact that this equation, right, equals 0 has no solution. So these are the two that are synonymous with a function having no zeros. The correct answer is E. Okay. And again, you might want to go back and look at your warm-up. That was actually given to you earlier in the exam. By the way, if you tried both A and B, those are just blatantly wrong. If we have x cubed plus 3, that does have a 0, right? It's looking like this. There's a 0 right there. And 0 is equal to x cubed plus 3. That also has solution, right? So x would be the cube root of -3. So both those are out. Okay, number 40. The graph of this guy, consider the graph. Well, we have it over here on our calculator. If graphed on a calculator, it appears to be a parabola. Yes, it does. Yet the graph is not a parabola, but rather a parabola with one point missing. What are the coordinates of the missing point? And there's a hint. The missing point is very close to -2.001. Let's see if we can trace -2.001 as the x. And the functional value is 12.006 and some change. So the answer here is C. Now, there's a couple things we can do on the calculator to sort of see this. First of all, let me zoom to a decimal window. Decimal windows are interesting because if you look at the x values I'm tracing here, you see they go down by tenths. Look how the x is changing, going up by tenths. However, we do want to go all the way up to 12, so let's tweak our y values. Let's go up to 15 just so we can see it. And here's the graph. And sure enough, you see there's a gap. There's a point that's missing. And if we trace along, we're moving along. When we get to 1.99, we're okay. When we get to -2, there is no calculated value. And then when we get to -2.1, there is. Okay? Interesting graph. The graph has an infinite number of points, which is not one of them. Well, we just figured out which was not one of them. It was, in fact, -212. In fact, you could, if this is our function, x cubed plus 8 over x plus 2, you could, in fact, verify that all these other ones are legit. If we put 1 in, this is the first guy, we would get 1 cubed plus 8. Over 1 plus 2, which is 9 over 3, which is 3. Okay, so that's certainly a point. If you put 2 in, I'm not going to do all of these, but you could do it on your own. 2 cubed plus 8 over 2 plus 2, and that's what, 8 plus 8 is 16 over 4, which is 4, so that's a legit point. However, if we try -2, and we actually work that out, we find we do not get a value. F of -2. We get -2 cubed, right, plus 8 over -2 plus 2, right? So this is substituting -2 in. -8, I don't know why I don't have an extra set of parentheses there. We get -8 plus 8 over -2 plus 2, which is 0 over 0, which is indeterminate. That does not give us a real number value. This point is not on the graph. Okay. And lastly, we'll stop here. This is factoring a sum or difference of cubes. Select the correct statement. As you go through here, you will find the correct answer was E. So we have A cubed plus B cubed, A plus B, A squared minus AB plus B squared, and then A cubed minus B cubed, A minus B, A squared plus AB plus B squared. just note that this, if we jam these together, a plus and a minus, the pluses all go together. And let's do this in black. The minuses go like that. Okay, so if you start with the minus, the first binomial has a minus and the trinomial starts with a plus. If you start with a plus, the binomial has a plus and the trinomial starts with a minus. And that's what this says. Okay, let me go ahead and stop this one here, and we'll pick this up again on problem 43.